Yeah, welcome everyone. This is, I think, our second or third session of the day. I'd like to welcome Eduardo and John from HCL. Hopefully it'll be a good hour on mainframe integration architectures. So welcome to both to the app dev track, and off you go. I will be quiet and sit in the background.
Thanks.
Thank you.
I'll
Thanks,
watch
Louisa.
the chat for you as well.
Okay. So my webcam seems to be suffering from a latency problem, but I am here even if I'm not moving. So today's topic is achieving code reuse across different mainframe integration architectures. So we're talking here about architectures or topologies used to connect client applications to services that run on the mainframe. Next slide. So your main speaker today is Eduardo Lupi, who is the DevOps lead and the VS Code solution architect for our team. My name is John Caperton. I'm the development manager of the team, and we're from HCL Software, which is a division of HCL Tech. So HCL develops several IBM products, software products, under IP partnership agreements. Our team develops two of the IBM mainframe products, IBM Fault Analyzer for ZOS and IBM File Manager for ZOS. So we have a team that develops the actual mainframe products, and then my team develops the client interfaces. So we have an Eclipse GUI for both products. It's been around for a number of years, and we're in the process of developing VS Code clients for those two products. Next slide, please. So today's topic is about our use of Kotlin in these new VS Code clients to address the issue shown here, the skills change and learning curve that was involved in moving from Eclipse and Java to VS Code and the web stack. Our desire to maintain the same sort of development velocity that we had with Eclipse releases. And most importantly, our desire to reuse code across different client architectures that we might adopt in the future without having to rewrite large sections of code for different platforms. Just to clarify, the presentation is not about Fault Analyzer and File Manager or the VS Code clients, other than to provide some context that you'll need to understand the main topic. Next slide, please. So this is the agenda for today's presentation. I will start by providing some of the context that you'll need. I'll describe the challenges that we faced when we moved to VS Code and the choices that we made. Then I'll hand over to Eduardo, and he'll start with an overview of VS Code extensions for those that are not familiar with them. Then he'll explain why we chose Kotlin to address those challenges. And then using some code examples based on a design of our FM solution, he'll explain how and where we use Kotlin. And then he'll finish with a DevOps discussion where he'll explain how we use our Git repository and our continuous integration build system to handle a multi-language solution. Next slide, please. Okay, just very briefly on the two products. Fault Analyzer is a product that runs on the mainframe. It helps you determine the cause of an abend. So it will analyze abend information that's produced by ZOS or the subsystems that run on ZOS and produce something called a fault report, which explains what happened and why, which program abended, which line of source code the abend occurred at, and if any variables were involved, what their contents were. There are three interfaces for Fault Analyzer: an ISPF interface, an Eclipse GUI, and a batch interface for high volume work or long running tasks. The screenshots on the right show what life is like with and without Fault Analyzer. So on the left is a shot of a IPCS formatted dump, which a programmer would have to navigate and understand hexadecimal data if they wanted to diagnose an abend from a dump. Fault Analyzer will do that work for you and produce a fault report as shown in blue on the right, and that's a formatted report that tells you what the abend was, which program abended, and down the bottom you can see some information about the line of source code and the variables that were involved. Next slide, please. So File Manager is a mainframe program that simplifies access to mainframe data. The diagram on the right shows the different types of data stores on the mainframe, different types of ZOS data sets, Unix files, and subsystem data in databases or systems like KICS and MQ. Each of these have their own access method or API or utility program. And to access the data, you need to understand all of those access methods. So File Manager hides the underlying access methods and simplifies that complexity by providing a common editor and utilities for manipulating the data without having to understand the access methods. It includes the concept of record templates, which are like copybooks in languages like COBOL or PL1 that identify the fields within a record, the data types, any formatting requirements. And it has three interfaces as well, so an ISPF interface, an Eclipse GUI, and a batch interface. Next slide, please. This is the architecture of our existing Eclipse clients. So we have plugins for Fault Analyzer and File Manager that extend the IBM Explorer for ZOS and IBM Developer for ZOS platforms. These plugins use a proprietary socket interface with internal FA and FM APIs to talk to FA and FM on the mainframe. We have a process called the common server, which runs as a started task in its own address space, listening for client requests. When it receives the request, it starts FA or FM in a separate address space and hands over control of the client socket so that FA or FM can communicate directly back with the Eclipse plugin. Next slide, please. Okay, when we moved to VS Code, there were some constraints that we had to work within. So we had to use the existing socket interface. We had to reuse the existing Fault Analyzer and File Manager internal APIs. And we could not make any changes to the host products, FA or FM on the mainframe. Next slide, please. Some challenges that we faced with VS Code. One of the big ones was the technology paradigm shift. We had a team that were experienced in Eclipse and Java, moving to VS Code and the web stack that's based on JavaScript technologies, HTML, CSS. We wanted to deliver our VS Code clients as quickly as possible, in spite of that learning curve. And most importantly was reusing code across different client architectures in the future. Okay, so let's deal with that last point about reusing code. These two diagrams show a 2-tier and a 3-tier architecture. So these are the options for our VS Code clients. On the left is the same diagram you saw for the Eclipse clients, only VS Code is the client in this case. On the right, there is a mid-tier web application that is acting as the socket client to the mainframe, and it will transform the internal APIs and the XML data into REST services and JSON data, which then can be consumed by the VS Code client. Now, the 3-tier solution on the right is more effort to develop because we have to create that transformation layer, but it does give us the flexibility. Next slide, thanks, Eduardo. It gives us the flexibility of being able to introduce other applications or programs that can consume FA and FM services through REST. So the red ellipse that says integration is the main point of this slide. That represents integration code. And that's a large part of our client application development. So some of the development is user interface functionality. A lot of it is infrastructural plumbing code, serialization, communications, data transformation, and so on. And it's that code that we wanted to be able to reuse across different client architectures. Next slide, please. So these are the decisions we made. We chose a 2-tier architecture because it offered the same topology as the Eclipse client, which we know is tried and tested and robust. It's a familiar configuration for existing customers. There's no server-side changes on the mainframe. And from a development perspective, it was the least amount of effort because we didn't have to develop that mid-tier transformation logic. And we chose Kotlin to achieve code portability. So this would allow us to reuse code from our 2-tier solution in any possible future 3-tier architectures. It also offered a faster learning curve for our Java developers. Next slide, please. There's some background on Kotlin. I won't go through all of it, just to point out that it's specifically Kotlin multi-platform that we use. which is a Java-like language that compiles to multiple platforms. And the two platforms that we were interested in were JavaScript for the two-tier solution, and for a possible three-tier solution in the future, Java or the JVM. Kotlin was open sourced under the Apache 2.0 license in 2012. Next slide, please. Okay, that's me done. I'm now going to hand over to Eduardo. Thanks, Eduardo.
Thanks, John. Thanks, John. So hopefully everyone can hear me. We have seen what file manager and fault analyzer are. We have seen what we want to do with VS Code now, and we have seen the current architecture that we have in Eclipse. I think before diving into the main topics of the presentation, it is better to have an overview of what the VS Code platform is. So VS Code is built over the Electron framework, which is a framework that allows us to create desktop applications using web technologies. Usual HTML, CSS, and JavaScript. Because of that, it uses both Node.js, which acts as a sort of local backend, and the Chromium browser engine, which is used to render UI elements on screen. It is almost entirely developed in TypeScript, which is obviously then compiled down to JavaScript so that it can be executed inside of Node.js. And it is an extensible platform. So it is extensible with a plugin mechanism. And in VS Code terminology, a plugin is also called an extension, but different terminology, same concept. So what is an extension? Comparable to an Eclipse plugin. As I said earlier, same concept, just a different name. So what it can do is it can contribute new behaviors, or it can modify existing behavior. So it can, for example, add trees, tables, panels, new types of editors. It can contribute new language supports or enhance existing language supports, and so on. And an extension is also typically written in TypeScript, because then it can easily interoperate with the base platform. Now, this is how I like to split up an extension in three main parts. The extension code, which is the core part of the entire package, and it is what can programmatically interact with the VS Code API surface. So it can handle commands, modify settings, and basically use all of the, as I said earlier, all of the APIs that VS Code exposes. Then on the bottom left, we have web views, which is what allows us to display totally custom UI elements inside of the VS Code frame. A web view is just the typical HTML, CSS, and JavaScript combination, although you'd normally pick a web framework to develop them. So something like Angular, React, or Vue.js. And then we have what I like to call supporting libraries. So those are pieces of software that are not dependent on the platform itself, but typical libraries that you can bring in via package manager, or libraries that you developed locally in the same workspace as the extension code or as the web views. And again, our goal here is to replicate the functionalities that we have now in Eclipse and make them work inside of VS Code. And we are going to do that through the extension mechanism that we have just explained. And also we are going to do that by extending another extension, which is Zoe Explorer for VS Code, developed by the Open Mainframe project. And we do that like what we did for the Eclipse solution with IBM Explorer for ZOS, because Zoe Explorer gives us a foundation. It gives us the basic features like exploring datasets, opening members, or creating mainframe connections. That's why we want to use it. Now, before jumping into coding immediately, as a typical programmer like me will do, we have to find what our core component is, what powers all of the functionalities that we have currently in Eclipse. And that core component for us is our protocols. We have a couple of custom protocols, one for file manager and one for fault analyzer, that we use to exchange data with the mainframe. And both of them both of the protocols use TCP sockets to exchange data. So they serialize commands and then they synchronously await mainframe responses. That's how they work. And we expose those protocols through higher level services to platforms like Eclipse or VS Code. So what we have to implement first is this core component, those two protocols. Now, unfortunately, the two protocols are not just about serializing and deserializing streams of bytes. They handle some complexities behind the scenes, and some of them are highlighted here. So for example, we serialize and deserialize data using ABCD char sets, which are specific to mainframes. And ABCD char sets are easy to use when you are developing over the JVM because they are typically provided by JDK implementations, but it's not the same for other platforms. For example, in JavaScript, you don't have access to ABCD char sets. You typically handle everything in UTF-8 instead. So here we have to roll our own implementation. Then we parse some of the data that we receive from the mainframe. We have custom languages pretty much with custom grammars that generates lexers and parsers. We perform text diffing as an optimization mechanism internally. And we also handle XML documents. So we read and write XML documents both in memory and on the file system. And now you start seeing that we have a lot of functionalities that we have to re-implement, and implementing all of them may translate to a big initial effort. And we have also to consider that our team's experience is mainly focused on Java and on the JVM. So it's probably better to ask ourselves a couple of questions. The first one is, can we keep writing Java? Because we are comfortable with the language, we are comfortable with the tooling for that language. So if we could reuse it for the extension code, it will probably speed up quite a lot the development process. Now, the short answer is no, because as we have seen earlier, VS Code doesn't run on the JVM, but it requires JavaScript. The longer answer would be probably by having a separate component that we ship alongside the extension code. Now, this increases the overall complexity. So maybe that's not what we want to do, but let's assume that we can do it, that we can keep writing Java. The next question is, can we reuse existing code? And again, the short answer is no, because unfortunately, most of the code that we have for those two protocols is tightly coupled with the Eclipse platform. The longer answer will be probably yes, although it means that we don't only have to extract the code, we have to extract many of the Eclipse dependencies. So again, assume we can do it. And the last question is, can we deploy that code to the browser? Because VS Code is not just a desktop app, it can run inside of a browser, and the same is valid for any VS Code extension. So can we use it inside of a browser? And here the answer is just no. There is no short or long answer, because first, we are using TCP sockets, and TCP or UDP sockets are not available inside of a browser for security reasons. And second, because again, we will have to ship that Java component separately. So an install workflow will be to first install the extension inside of the browser VS Code instance, and then the user will have to download that Java component, install that Java component, and we will have to find a way to communicate between the extension and the Java component. So added complexity and not a nice user experience. So the answer to all of those questions is no, and that can be a problem, because what do we want to do? Do we want to spend weeks or potentially months exploring the web stack with new languages, new tools, an entirely different development experience? And that means we have to delay the implementation of the new extensions in favor of learning first. So what if we can find an alternative to that. Maybe something that gives us a way to implement that core component, those protocols. And then while we are implementing that, we also learn about the web stack. Now that alternative should give us JavaScript output because it's essential for VS Code. It should give us a development experience similar to what we have now in Java, maybe a similar syntax, maybe similar tooling, similar build tools, and something that has a rich SDK because we are used to the JDK. We are used to have pretty much everything we need in a single place, and we don't want to lose too much time looking for third-party dependencies because those third-party dependencies require maintenance effort. And then most importantly, what we want to obtain is code portability. And code portability for us is important because we don't want to fall into the same trap as the one we fell into for the Eclipse development. So for Eclipse, we built code that was tied to that specific platform. And we don't want to make the same mistake. We want something that is totally independent from any particular solution, and something that we can potentially deploy to multiple different platforms and multiple different architectures. So we can visualize what I mean with code portability with the following slides. Now, this is a typical two-tier architecture where the client talks directly to a server. And consider that blue cube as our piece of software. We may want to deploy it to a client. We may want to deploy it as a service that supports that client. For example, a native binary or a browser plugin that then talk with the extension via some kind of native messaging. Or we might want to deploy it in a middleware. So if we switch to a three-tier architecture, we don't want to rewrite any code. We want it to work straight away. Or we might even want to deploy it to the server directly. So the key word here is flexibility, freedom of choice. And that's what ultimately led us to choose Kotlin. We have seen a bit of Kotlin's history earlier with John, but I think most of us know Kotlin because it is widely used in the mobile world, especially for Android. It is the default language for Android since 2019, and it has been growing in popularity year by year. So again, we have chosen it because it is similar to Java. It has a similar syntax. It uses the same programming concepts because it uses Gradle as its build system, and Gradle is also used a lot in Java world because it has a rich standard library, and we have seen that pretty much everything we need is indeed contained in the standard library. And lastly, because it gives us that code portability that we want, because it is effectively multi-platform. So what is Kotlin multi-platform? Multi-platform is a technology that allows us to write code once and then compile it to multiple different representations. Now, how does that work? The Kotlin compiler has multiple backends. So if you pass the same code to those backends, you get multiple different results. If you want, let's say, WebAssembly code, you pass that code, that Kotlin code, to the WebAssembly backend, and it outputs WebAssembly instructions. Same for the JS backend, which outputs JavaScript. Then the JVM backend, which outputs bytecode, and then the native backend, which uses LLVM to output native binaries, so with OS-specific instructions. And here we have, in this example, we have a hierarchy of targets with the first one, the top level one, being common. It's not really a platform, it's just a way to separate, like to know that when we code in the common layer, we can potentially compile for all of the platforms that Kotlin supports, which are 20 plus. So if you look on the right side, I've written generic at the top right and specific at the bottom right. And That means the common layer is the most generic one, and it doesn't have access to any platform-specific APIs, if not through the standard library. And as we go down the hierarchy, we have access to more and more specific and more platform-specific APIs. So on the second level, we start having access to WebAssembly APIs, to Java APIs, to JS APIs, and to POSIX APIs in case of native. And if we go down further, for example, on the native side, we start having access to Linux-specific APIs or to Windows-specific APIs. That's how Kotlin multi-platform works. But again, most of the code that we want to write must be contained in the common layer because we want it to be compilable. We want it to target as many platforms as possible. And this is the design, the code design that we ended up with. So at the top, you can see that we have our VS Code extension that communicates with the Kotlin code. That is the bulk of our code. And then again, at the top, we have a potential web application, a middleware that is developed in Java or in Kotlin, doesn't matter, but it runs on the JVM. And again, it still references the same code, the same Kotlin code. So that big Kotlin box is split in two parts. The upper part is the common code, and the bottom part is the platform-specific code. And you can see that the common part is the bigger one. So we expose a couple of services, one for file manager and one for fault analyzer, which act as our APIs. And those services internally handle all of the complexities that we highlighted before. So parsing, text diffing, XML manipulation, serialization, and deserialization of byte streams. And then we have that thin layer of platform-specific code that handle our TCP socket implementation. So unfortunately, each platform uses different APIs to interact with TCP sockets. So there was no way to make that code common. But out of all of the code that we have, that is just a 10% maybe. So we have a socket implementation for Node.js, a socket implementation for the JVM, and then potentially we could plug in a WebSocket socket adapter in case we want to target the browser. And that platform-specific code is then plugged into the common code. That's how our code architecture works. And effectively, this design allows us to move the Kotlin component around the architecture's node. So we can see here that we have, again, a two-tier solution. We have our Kotlin component on the client side. We can move it to a supporting service. So we can compile using LLVM, for example, or we can move it in a middleware application and we can compile it to bytecode and execute it on JVM, or compile it to JS and execute it in a Node.js application. It's the same. We don't have to change the code. Only the TCP code is platform specific. And this is how we are currently handling the two-tier solution. The extension code is developed in TypeScript. Web views are developed using Angular. And then we have that single supporting library, which contains the protocols implementation that is developed in Kotlin and is locally developed. So basically, all of those three components are inside of the same workspace. But we will see more on this later. Before that, let's go through a very basic example of a multi-platform library. So how you can build a Kotlin project yourself. And this requires a bit of Gradle knowledge, although the examples are extremely simple and should be understandable even if you have never used Gradle. So let's start with a very simple Gradle build script. You can see that we have an application that is named KMP-GSC, our Kotlin multi-platform library, and the build script simply defines a group and a version for that application. Now, a small detail before going on with the example, the build script itself is written in Kotlin because Gradle is transitioning away from Groovy towards Kotlin, just because it's a safer language. It's nicer to write Kotlin compared to Groovy. But let's keep going with the example. So we have this basic Gradle build script, and what we do now is we add the Kotlin multi-platform plugin. You can see it at the top of the build script. And now we are effectively ready to instruct Kotlin on which platforms we want to target. So since we are most comfortable with the JVM, let's target that one first. And that's how you do it. It's extremely simple, just 3 lines inside of our build script. And we are pretty much ready to code now, because Kotlin knows that that it has to compile our code down to bytecode. So here is a very simple example, a mock of a real service that we have in our code. On the left side, you can see that we have a file manager service.kt file under a common main source set. If you recall the target hierarchy that we have seen earlier, the common layer is at the very top, and it's the most generic one. So if we have code under common main, it means that code can be compiled for all of the platforms that Kotlin supports. And inside of that file, we have a file manager service class with a get service level method. And then we have a top level, a file level, a process level function that simply returns the parameter, the level parameter. Now, you can see there is a bit of difference with Java in the sense that Kotlin gives us a bit more freedom compared to Java. You couldn't have a top level function in Java. It would have had to be contained inside of a class, but that's another topic. Just wanted to point that out. Now, if we want to test that code to execute it so that we can verify it effectively is built for the JVM, the fastest way to do it is to add a test case. And that's how you do it. You add a new class under the common test source set with a test case named service level. And inside of that test case, we simply instantiate the file manager service. We call that get service level method, and we assert the method result. Now, if we want to run it, we can simply click on the ID Gutter runner icon, this one, which by the way is inside of IntelliJ IDEA. You click on that icon, and what happens is Gradle executes all of the correct tasks that target the JVM. And you can see that because on the left side, on the test tree, it's evident that it is targeting the JVM, and the same is valid for all of the Gradle tasks. At this point, we have our common code. We are targeting the JVM. But what if we also want to target JavaScript? Because that's one of the platforms we are interested into. And that's how you do it. Another 4 lines inside of the build script where you activate the JS target. You specify under which runtime that JS code will run on. That is Node.js. And you specify the output of the compilation process with binaries.library. That means the Kotlin compiler will output a Node.js package. So some JS files and a package.json file. If we go back to the test case and we try to execute that test case again, it won't run immediately under the JVM, but we will have the choice to select another platform, which is JS in this case. And if we click on JS, again, Gradle will execute our test case, but this time it will be executed under Node.js. So you see on the tree, on the test tree, and also on the Gradle tasks that they are prefixed with JS, and some of them also with JS Node. And we can keep adding more platforms. Like On the example on the left side, we have activated WebAssembly with JavaScript interrupt, WebAssembly with WASI, Windows support, Linux support, and if we go to execute the test case, all those activated platforms are immediately reflected in the run pop-up. All but Linux, just because my host laptop runs on Windows, and obviously it cannot run Linux binaries. So up to now, we have all of our code under common. But what if we need to access some platform-specific APIs? To do that, Kotlin gives us the expect actual feature. So expect actual declarations. And what it means is, if we look at the example, we simply mark a function like the process level function with the expect keyword. We remove its body because effectively now it's just a signature that we can keep using on the common code. And then we we have the actual implementations on platform-specific source sets. So as you can see here, on the right side of the image, you can see the file tree. We still have the file manager.kt file, service.kt file under common main, but we also have another couple of files. So one is under JS main, the other one is under JVM main. And if we look at the implementations of those two files, so in the middle, you see the JS one, and you see that we are accessing a node property. And if we look at the JVM one, you can see that we are accessing the JDK system class that are indeed both specific to their platforms. So straightforward. We have seen how to code in common. We have seen how to use expect actuals, but our use case here is we want to export that Kotlin code so that it is visible from our VS Code extension. Now, recall the code design that we have seen earlier, where we had our extension at the top that was referencing the bulk of the code in Kotlin, the file manager service and the fault analyzer service. So how do we export those services so that they are visible in JavaScript? This is split in two parts. The first part is configuring the Kotlin toolchain correctly. And the second part is setting up the development environment in the most optimal way. So for the first part, one of the two features that Kotlin gives us is the JS export annotation. What that annotation does, and by the way, we can apply it to any top level declaration, like our file manager service class in the screenshot below. What that annotation does is it instructs Kotlin not to change names, not to mangle names, or not to perform dead code elimination on that specific code path, just because by default, what the Kotlin compiler tries to do is minimize the outputted JS bundle size. But obviously, we don't want that, because even if we are not using this service on the Kotlin side, we still want it to be usable outside of the Kotlin world. We want it to be usable in the JS side. So we apply JS export, and then we also activate the generate TypeScript definitions features. And we do that through the Gradle build script. What generate TypeScript definitions does is it instructs the Kotlin compiler to generate an additional file containing a series of TypeScript definitions, one for each code, for each piece of code that has been marked with JS export. And if we build our project again, our KMP-GSC library again, we can see that we have an additional file under the outputted production library, kmp-gsc.d.ts, which stores the signatures of the JS exported declarations. So no body, no implementation, just the signatures. And this mechanism is basically comparable to headers file in C, where the only use is understanding how to use the API that we have exposed. The second part of the process is allowing that JavaScript code that we have exported with JS export and generate TypeScript definitions, is allowing that code to be imported from the JavaScript side, so specifically from our VS Code extension. And to do that, we can set up the development environment in a certain way. Now, there are multiple ways to do it. It will take probably 1 hour just to go over all of them. So what I've decided is I'm going to describe just what we did in our case. And what we have chosen to do is use a Git mono repository. So imagine starting with an empty repository and then simply moving inside of that repository the Kotlin multi-platform project sources. So Kotlin code built by Gradle. And then we also move in the VS Code extension project, which includes the TypeScript sources and possibly multiple Angular web views or even multiple supporting JS libraries. Now, the problem here is how do we depend on the Kotlin multi-platform project from the VS Code extension? They are different technologies, so how do you do that? Well, the first step is to compile or to build our multi-platform project so that we get our JS files. And by default, the compilation process outputs those files under that Kotlin multi-platform project folder, specifically under build dist JS production library. So a naive solution could be to npm install or npm link that production library directly. So through a relative or an absolute path, you would npm install from the VS Code extension, and then you'd have access to the JS code. Now it works. It's a simple solution. However, it has a huge downside, and that is every time you change your Kotlin multi-platform project and you recompile it, you have to npm install or npm link again. Otherwise, the source changes are not reflected immediately on the VS Code extension side. Like you don't see the changes. You effectively keep working on an outdated state. But we can do better than this. So the first step is we instruct Kotlin to generate the JS sources at the root of the repository. So as you can see on the right side, I'm instructing Kotlin to generate the distribution code under a generated -packages folder. And if we visualize, what that does is the following. So on the left side, you can see the updated example. Kotlin multi-platform project builds JS sources, and those JS sources are now at the top level of the mono repository. Now, obviously, you don't want to version those sources. So what you can do is you can git ignore the entire directory. That's what we did. But the concept is now we have a well-structured workspace. So the next step is transforming this mono repository into an npm workspace. We simply add a top-level package.json file. We add all of the JS projects that are part of that workspace, like you see on the bottom right. And then from the VS Code extension side, we can simply depend on the compiled kmp-gsc application or library. We use a special notation with an asterisk to indicate that we are not installing anything. We simply want to depend on what is inside of this npm workspace. It's straightforward. And now when we compile again the Kotlin multi-platform project, the new sources, the new state is immediately visible on the VS Code extension side. At this point, we have our mono repository configured. All of our sources are inside of the mono repository, clean state. We can at that point start developing, and the development experience is not the best, but not even the worst. But we can make it again better. So current problems are all of the projects that we have in the mono repository are built separately. So first we have to build the Kotlin multi-platform project so that it outputs the JS sources. Then we have to build the Angular web views and all of the JS supporting libraries if we have them. And only at that point we are allowed to build the VS Code extension. So there are multiple commands involved to get the final artifact or artifacts. And you have to remember those commands each time. So there is a specific sequence. Now, you could say just write another script, which in turn calls all of those commands. It works again. It's a simple solution. But the problem is you are missing out on the dependencies concept. Like you have your sequence of commands, but you don't understand, you don't know that the VS Code extension project depends on something else. It's you know it because you have probably coded it, but if there is a new developer, it's not immediately obvious that there is a link between projects. So there is definitely an optimal way to do it using a proper tool. And that tool is NX. So NX is a build system that is specifically focused on mono repositories, and it can handle mono repositories of any size with any sort of technology. So what NX gives us is plugins. We have pretty much a plugin per every supported technology. And if we look in the middle of this image, you can see that we still have our mono repository, our multi-platform project, our VS Code extension project. And for each of them, we are using a separate plugin. So for the Kotlin project, we are using the NX Gradle plugin. For the VS Code extension project, we are using the NX.js plugin and the Angular plugin because of the web views. And what a plugin gives us are executors, which are basically task runners. Each plugin carries some executors that are able to build or to run a specific technology. And a plugin also contains generators, which allows us to create scaffoldings. For example, if we want to create another JS library or another Angular web view, another Angular application, we can use an NX generator from the Angular plugin or from the JS plugin, and that generator will output a basic implementation of a JS library or of an Angular project, and then we can keep developing over that one. It's definitely nice to have. And what generators do is they automatically link that created library or project at the root of the workspace. So basically, when you create a project through a generator, NX is immediately aware that that project exists. Otherwise, you may have to fiddle a little bit with configuration files. Then what NX gives us is task caching. Since NX sits on top of other build system or other build tools, it is able to intercept the output of those build tools. And now imagine that we have 20 different projects inside of our mono repository, which is very realistic because we have around 20 projects at this point. Imagine if every time we want our final artifacts, we have to build all of them again. We might lose a lot of time, a lot of build time, both locally and on our CI VM. So what NX does is it intercepts the build result, and then it is able to understand if the source code that is associated to that build result has been changed or not. Now, might happen that out of 20 projects, you only modify a couple. And at that point, NX knows that 18 of them aren't changed, haven't been changed. And so it will simply take out the last result from the cache and only execute 2 of them. You can bring your CI times down like from 30 minutes, 40 minutes to 5 or 6 minutes. And then another nice feature is project tracking. So what we see here is a part of a real NX project graph taken for our FA fault analyzer VS Code extension. And you can see that the FA WebView fault report project depends on FA UI components, and it depends on FA UI services. This is knowledge that comes from the NX tool. So NX knows that if we want to build the fault report project, we first have to build FA UI services, and then FA UI components, and only then FA WebView fault report. And this is valid for all of the projects inside of our mono repository. So NX drives the build process by itself because it knows what we are using, the inter workspace dependencies. And then as a bonus point, what NX gives us is plugins for our IDEs. So we have NX Console, which is a plugin available for both VS Code and IntelliJ IDEA. And that plugins pretty much allows us to get rid of the command line interface and simply do everything inside of the IDE. So we can use generators, we can use executors, we can visualize the project graph all inside of the IDE. We don't have to switch to a terminal line. And yeah, that's it from my part. Thanks. So John,
thanks, Eduardo.
No problem.
Yeah, thanks. Okay, so just to summarize, we went through the FA and the FM client architecture to set the context, discuss some constraints, challenges, and decisions. Eduardo took you through an overview of VS Code extensions. Then we discussed why we chose Kotlin. We looked at how and where we use it, and finished off with a discussion about JavaScript interoperability via our mono repository and the use of NX. So I hope that was useful and interesting for you. We're happy to take any questions now.
Thank you for your session, guys. I
you.
don't see anything on the chat.
Okay. Well, thank you.
Thank you.
Yes, thank you so much. And as we said,
Cheers.
this is being recorded, so at least you'll get the recording afterwards.
Thanks.
Great. Thanks. Thank you all.
Thank you so much.
Bye.